Hey everybody, it's Mr. N, and we are going to do volumes, but by cylindrical shells this time. Cylindrical shells. Typically this is not an AB topic. They'll only cover it in BC, but I do like to cover it in the AB classes just to make sure you understand it because it is a useful concept. So here's where we use it. Suppose we had this equation. Y equals 2x squared minus x cubed and y equals 0. So we're bounded by this parabola, or this cubic function, sorry, and y equals 0. And we want to find the region bounded by these rotating about the y. So in this case, we're going to rotate this way, about the y. Well, we have our radius, our little radius, and our big radius. So our thicknesses would be dy over here, and I'll write it down, dy, which means I need this equation to be in terms of y. In terms of y. Well, good luck solving that. Good luck solving that for x because you won't be able to. So, since we can't, we still need to find a way to be able to do this problem, and this is the method we're going to use. It's called cylindrical shells, and it's based off the following situation. Suppose you had a hollow cylinder. So if I rotate this around, I'm creating this hollow cylinder, and I've got this larger radius and this smaller radius right here. And I want to find the thickness right in here of this shell. Well, we take our outer radius and our inner radius, find the volume of the outer, subtract out the volume of the inner. So I'm finding the whole thing and taking this whole out, and I'm left with this thin shell. Now, expressing this in a formula, pi r2 squared times h minus pi r1 squared times h. Both h's are in common, so I can take that out. They both have the pi in common, and I'm left with this situation. r2 squared minus r1 squared. And that's going to give me that thin shell. Okay, so let's continue on, and we're going to rewrite this. Here's what we're going to do. You have r2 squared minus r1 squared, and I'm going to factor this. This becomes right here when I factor it. That's the little trick. All I do is factor this, and I end up with r2 plus r1, r2 minus r1. r2 minus r1, though, is that delta r, which is this thickness. The r2, the second radius minus the first radius, that's just this delta x thickness, that delta r that we're going to call. So that's my thickness. There's my delta r. So I'm going to substitute this back into this equation that I have developed right here. Let me highlight it for you guys so you can see it. So I developed this equation right in here, and I substitute that, and I'm going to substitute this value right there. Well, r2 plus r1, that's just 2r. Well, the question is how did I get this 2r? Okay, so if we call r halfway, because we had r1 and r2. So if I call r halfway, the average between r1 and r2. So r is going to be 1/2 r2 plus r1, which is that. Because remember, r2 minus r1 is our delta r, which we called our thickness, and our average could just be the regular r, which is r2, to r, which is equal to r2 plus r1, right here. Right, bring the 2 over to the other side. So I end up with this final equation right here, where this is the circumference, right, 2 pi r, my height is h, and my thickness is delta r. So putting all of that together, we could take the sum of these shells. So basically I'm going to add up all these little shells that I've created to get this volume. So the volume, and this is for a vertical axis of revolution, is going to be the integral from, notice, instead of going perpendicular to the axis of rotation that we did with washer and disk methods, we are going to be parallel. So if this is a vertical axis of revolution right here, notice I'm parallel to it. So it's the opposite. Just think of it. The other way we couldn't solve it directly, so in the shell method, we're doing the opposite. Over here, this is parallel to that, and I'm going to go around this way. So then that means I'm going to take the integral from here to here, and my slices are still dx, but I'm going in this manner, right? And I need them to be dx. Remember that original one? We couldn't solve for x, so we had to have it in terms of x. So I still need it as dx, and this is going to be this equation right here, 2 pi. I'm just going to call the x the r, and then my f of x dx. So 2 pi x times f of x dx. dx is the thickness, x is the average radius, f of x is the height. Just always draw it out. Always draw it out. Remember, for cylindrical shells, you want to be parallel. For washers, you want to be perpendicular. And that's the difference between the two. When should you use which one? Typically, always go washer and disc method first. If that doesn't work, then go to shells. But a lot of times you'll notice that shells will sometimes, not a lot of times, but sometimes be easier, just depending on the problem. All right. So let's generalize this a bit. If you are rotating about a line, not an axis, you're going to say the integral from A to B. Right here, let's indicate these. This is A, there's B. And in this case, it'll be 2 pi, this line minus x, f of x dx. Now note, if your curve is on the other side of the line, you're going to say x minus the line, because the line will be smaller. So you're just basically saying bigger minus smaller. Now, so suppose we need a horizontal axis of revolution. So again, we're going to go parallel. This time, A and B end up on this side from A to B, because we're taking our slices to be parallel to this horizontal axis of revolution. And we'll need, since we're going this way, it's just like before, we have to figure out what our slices are. They're dy. Our slices are dy. So right here, but we're going dy with them this way. So we need the equation to be in terms of y. So we need f of y, and we need a y there. And same thing, if you've got different lines, right here, the integral from a to b, and if the curve is above the line, it'll be y minus the line. If the line is above the curve, then it's line minus y. This so that you end up with a positive value. All right, here are all the methods in a nutshell. Here's the disc and washer and the shell methods. Remember, for the disc and washer method, you want to go, if we're going this way, you want to go perpendicular to the axis of rotation. Perpendicular. Over here, if we're going in rotating it this way, perpendicular. However, if we do shells and we're going in this manner, we want to be parallel. Our slices are parallel. So here, our slices will be parallel to the axis of rotation. I'll have dx's. Over here, since I'm going this way, my slices are parallel to this axis of rotation, and I will have dy's. So you need to be careful, because the two methods require different things. One is perpendicular for disc and washer, and one is parallel for the shell method. All right, so now let's just go ahead and do some examples. Number 1 says, find the volume of the solid revolution formed by revolving the region bounded by y equals x minus x cubed and the x-axis about the y-axis. So let's graph this real quick. This is that first example that we were talking about, and it looks like this. And I've got this situation, and this crosses over here at 1, and that's 0. And I'm taking this and I'm going this way with it about the y-axis. So in this case, it's too difficult if I wanted to take my slices perpendicular to the axis of rotation like this, right? So these would be dy's, which would mean I need my equation in terms of y, but it's too difficult to solve for x. So we need to use the shell method, and in the shell method we're going to take our slices instead to be parallel to the axis of rotation. So parallel, which means I need dx's. So the volume, remember, it's 2 pi, the volume 2 pi x times f of x times dx, right? So the volume will be 2 pi times the integral. This is a, this is b, because I'm slicing it this way. So that's 0 to 1. And that's going to be x times my f of x dx. So 2 pi times the integral from 0 to 1 of x. Now my f of x is this x minus x cubed dx. I can go ahead and go through, and this ends up being, the volume is 2 pi times the integral from 0 to 1, and this will be x squared minus x to the 4th dx, which will give me, when all is said and done, 2 pi, and then here's the integral, 1/3 x cubed minus 1/5 x to the 5th on the bounds from 0 to 1, and that all comes out to be 4 pi over 15 cubic units. All right, taking a look at the next one right here. Find the volume of the solid of revolution formed by revolving the region bounded by x equals e to the negative y squared and the y-axis about the x-axis. So again, let's go ahead and graph this. And when I do, I will end up with a curve that's kind of like right here that I'm looking at. And I'm going up to 1 right here. And I'm taking this and I'm going to, about the x-axis, I'm going to take it in this direction, okay? So I'm taking that in that direction. Since I'm going about the x-axis, I need to take my slices, and this will look like this, take my slices in this manner, all right? And I'm just showing you part of the graph here. And I would need to have a dx, so I need this to be in terms of x, but we're going to say that this is too difficult to solve for y. So instead, let's erase this, and instead of doing it that way, I'm going to use shells, and I'm going to take these parallel to my axis of rotation, which would give me dy, which means I don't need to convert that equation. I could keep it the way it is. So use shells and dy. So the volume will be 2 pi times the integral. Now, since I'm going from here, the shells are this way, from 0 to 1, of x, or in this case it's going to be y, because I need this in terms of y, I need dy, and f of y dy, just like that. So this will be 2 pi times the integral from 0 to 1 of y, and now my f of y equation is e to the negative y squared dy, and as of right now I did not teach you the how to integrate e yet, so we're going to say use calculator. In other books they do show it to you a little bit earlier, so if you do want to do it by hand, just so you know, this comes out to 2 pi negative 1/2 times e to the negative y squared on the bounds from 0 to 1. But in any case, either way, this comes out to be 1.986 cubic units. All right, moving on to the next problem. It says, find the volume of solid of revolution formed by revolving the region bounded by y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. So let's go ahead and graph this situation like we always do. We'll start off with our graph. And this one, we've got this, and I've got right here x squared plus 1, so it's starting right here. We'll say this is at 1, and it's going up, and it's bounded by y equals 0, x equals 0, so right here, and x equals 1 right there. So this is at x equals 1. So it's this region, but I'm taking this region that looks like this, and I am revolving this about the y-axis, so it's going like in that manner. So I'm going to do this in a couple different ways for you. I'm going to do it with disc and washer first to show you the differences between the two. So now, if I was going to do this with a disc washer method, I would have to take this piece and break it up, and I can find this one around the y, but then I'd have to do this situation different, right? I would have to take the bigger radius minus the smaller radius, so basically take the whole out of it for this one and use washers on this one. So, since I'm going around the y, these would need to be dy. So this will be disc washer method, right? And I would need these to be dy, so I need these in terms of y. So I'm going to call this one region 1, and I'm going to call this one region 2. For region 1, the volume will be, now I need this equation, y equals x squared plus 1, and I need this in terms of y. So solving this would give me y minus 1, the square root, equals x, plus or minus, but I'm only concerned with the right side of the graph, so I'm only going to do the plus part right now. So the volume would be from 1 to 2, right? Because I'm slicing these vertically, and this is at 2 right there. That's where they intersect. So the volume would be the integral from 1 to 2. And I need a pi here. I could put it on the inside, but this will be big R squared minus little r squared, and this will be dy. So the volume will be pi from 1 to 2. The big R is this one all the way across, which is 1. The little r is the equation, right? There's your big R, there's the little r. So this will be 1 squared minus this root y minus 1 squared dy. Region 1 ends up being pi times the integral from 1 to 2, and this will be 1 minus y plus 1 when I clean it all up, right? Dy, and here, finishing this off, you'll get pi over 2. Region 2 will end up being the volume, and now here, this is region 2. All I have is one big radius, and all I have to do is rotate it around, which should be pretty easy. I mean, you could pretty much look at this and determine what the volume would be, because it's just pi from 0 to 1, and this will be 1 squared dy. So in this case, you will end up with the volume equaling simply just pi. Right, when we integrate that, we're just going to get 1 times pi. Adding these two up, you're going to get the total volume to be 3 pi over 2 cubic units. Now this was done with a disc washer method. So let's do it with cylindrical shells now, with shells. Now since I'm doing this with shells, I'm going to take my slices this time, and I'll kind of re-graph it here for you guys real quick. Looks something like this. I'm going to take my slices parallel, since I'm going this way, parallel to the axis of rotation. So those are my slices. And you'll see that in this one, it does not create two regions. So doing it in this manner, I'll get the volume equals 2 pi. Now, since I'm doing it in this manner, this is my A, there's my B. So this is from 0 to 1, the integral from 0 to 1. And over here, I'll have x times f of x dx, since my slices are dx like this. I should have said, I don't know if I said dy, but dx like that. So the volume ends up being 2 pi times the integral from 0 to 1 of x times x plus 1, or this is x squared plus 1, right here, dx. And this comes out to be 2 pi 0 to 1 of x cubed plus x dx, and that's going to be 2 pi times, this will be 1/4 x to the 4th plus 1/2 x squared on the bounds from 0 to 1, and that, when all is said and done, will give me 3 pi over 2, which is the same answer as I had there. All right, let's go ahead and do one more example. A pontoon is to be made in the shape shown. So it's made by rotating y equals 1 minus x squared over 16 about the x-axis from -4 to 4. So right here is the piece that I'm talking about, and we can put it on the axes here and say that this is like this and like that. Okay, and we are taking this top part right here, and I'll just kind of redraw it right here. We're taking that top part, and that's going from -4 to 4, right? And we're going to take this by rotating about the x-axis, so this piece is going in that manner, that direction. All right, so let's see what we could do with this. Since we're going in that direction, we can take our slices to be dx. So in this case, there's nothing really special going on here, and I'm not even going to use shells. I'm just going to go ahead and do this with a disk method because it's pretty straightforward. So the volume is from -4 to 4, pi, remember pi r squared, right? And here's my radius right there. That's it. There's nothing special about this. Don't use shells or anything crazy if you don't need to. So this is just r squared dx. So the volume here is pi from -4 to 4 of 1 minus x squared over 16 squared dx. And I'm going to say use your calculator on this one because I don't really feel like foiling that out. But either way, when you do that, remember, you could put the integral directly in there. You'll get 64 pi over 15 cubic feet. Okay, I have more to show you how we do this one. And the rest of these I'm going to post up for you guys in class. But I do want to do one more to show you how if it's revolved about a line. So let's just do this one. And we've got find the volume of the solid revolving the region bounded by y equals x cubed plus x plus 1, y equals 1, x equals 1, about x equals 2. So here's what the graph would look like. And we've got this situation over here, and the region bounded by this. So this comes out to be like that. I'm just quickly sketching this part of it for you. And like this. And we're revolving it about, this is at 1. And we're revolving it about 2, right over here, this line. And this whole thing is going this way, in that direction, okay? So notice here, we've got a space, right? So we've got a few things going on. Now, if I do this perpendicular to the axis of rotation, I would need a dy. But this is cannot solve for x in terms of y. And since we cannot do that, I'm going to take my slices in the other direction, and so I want these slices to be, instead of dy, dx, just like that. So, parallel to my axis of, in this case, my line of rotation. And since it's not the y-axis, I need to do this a little bit different. I need to say the line minus my x in this case, because this is where I'm shifted. And in this case, I also need to say my f of x, because it's not bounded, it's not touching that line, minus my line. But in this case, it's because I'm not on the axes, so this is f of x minus 1, and we're talking about this line, y equals 1. So this is because I'm revolving around this, 2, and the other one, so this one is 2 minus x, and this one is because I've got this space kind of here, and I'm not touching the x-axis, not touching the x-axis, so this is going to be y equals 1. So this is my x times my f of x in this case, because I'm going to use shells, right? That's what we had said. So in this case, this is the 2 minus x, and this will be f of x minus 1. That's what I'm going to put in each of these. So the volume will be 2 pi times the integral, so I'm going from 0 to 1, right? Those are my slices. And then, remember, it's always x times f of x, but in this case, it'll be 2 minus x, because it's my line of rotation right here. And then, on the other hand, I've got f of x minus 1, because I'm up off the axes and not touching the axes. So this is going to be x cubed plus x plus 1 minus 1, right? This is y equals 1. And this will be dx. So cleaning all this up, you can FOIL it out. You end up with the volume is 2 pi from 0 to 1. This will be negative x to the 4th plus 2x cubed minus x squared plus 2x dx. And to save you the headache, this ends up being 29, after you integrate and everything, 29 pi over 15 cubic units. Okay, we are going to do this one in class, but if you want to try it on your own and see what we end up with, this answer will be 124 pi over 5. Now, there are two ways to do this. You could do it with a washer method, in which you'll need 2 regions, or you could do it with a shell method, in which it's just 1 region, and it comes out pretty good. So I'll let you do that on your own, and we'll go over it in class. All right, so thanks for watching. Hit that like and subscribe button, and I'll see you guys in the next video.